we are uploading the code into the AdMega32P. So as you can see, there is no transmission going into the serial monitor. There's no transmission displayed because it's still in state A.
Now this circuit is in state A. So as we press this button, the transmission starts every 500 milliseconds, and the two LEDs, so the red one blinks at 1 Hertz and the green one is controlled by the potentiometer. And let's toggle the two red LEDs, 1 Hertz blinking. So as you can see, this is blinking when I'm holding it down. When I let go, it changes to the next red one. I can control the green LED's blinking frequency, also the servo motor. As you can see, the green LED is blinking at a lower frequency because the ADC value is high. Now if we turn to the notch to the right, you can see that the servo motor is rotating 180 degrees. Also, the LED blinks faster. And if I go back, the servo motor rotates to 180 backwards and the LED blinks slower. I can also toggle between state A and B. So if I press this button again, it should stop. So nothing is working and the transmission has stopped. But if I press it again, everything should start and this transmission should be starting again.
I also can toggle this transmission by pressing W for my family name. So if I press W now, the transmission is stopped. If I press W again, the transmission starts again. This is our state machine MCU project. I'm Ishan Wickremasinghe. My student number is 24638013.
I'm Ashwen Kugan, and my student number is 245564449.
This is the circuit diagram of our system. First off, we have the button 1 changing states from A to B and from B to A. The code snippet shown triggers the interrupt 0 vector ISR as button 1 has been pressed and released. This interrupt is associated with external interrupt 0, which is configured to trigger on any logical change. In the ISR, the button state variable is toggled using the XOR operator, changing the state from 0 to 1 or from 1 to 0, which effectively represents changing from state A to B and from state B to A.
Next, we have the LED sequence toggle, where at first the LED 1 blinks at 1 Hz and LED 2 is off. When button 2 is pressed but not released, LED 2 starts blinking at 1 Hz and LED 1 switches off. This is done by this code snippet, which triggers a interrupt 1 vector, ISR, as the button is pressed and held down. Inside this routine, the state of button 2 is determined by reading the state of the button 2 pin using pin D register and masking it with bitwise operation as shown. If the result is non-zero, it indicates that the button is pressed and held down. Button state 2 is set to 0. Otherwise, if the result is 0, indicating the button is released, button state 2 is set to 1. The main program loop later uses these button states to control the behavior of LEDs 1 and 2 as shown in this code snippet.
Next, we have the third LED where the blinking frequency is being changed according to the ADC reading from the potentiometer. Inside the timer 0 compare match interrupt, the code reads the ADC value from the potentiometer connected to pin A0. It starts the ADC conversion by setting the ADSC bit and waits for the conversion to complete. The ADC value is then stored in the ADC value variable. The code calculates the blinking period for LED 3 based on the ADC value. If the ADC value is 0, the period is set to 0 milliseconds. If the ADC value is 1023, if the period is set to 2000 milliseconds. For other ADC values, the period is set to the ADC value itself. Inside the same timer 0 interrupt, there is a static variable LED 3 count used to keep track of the elapsed time. If the button state is 1 or state B, and the LED 3 count reaches the calculated period, it toggles LED 3 by XORing the PB3 bit of port B. The LED 3 count is then reset to 0. If the LED 3 count is less than the period, it increments by 1. This implementation allows the potentiometer to connect it to A0 pin to control the blinking frequency of LED 3 when the system is in state B.
In the same interrupt routine, the code updates the position of the servo motor based on the potentiometer value, as shown in this code snippet. This scaling operation converts the ADC value, ranging from 0 to 1023, to a servo position value in the range of 0 to 180 degrees. The servo set position function is then called to set the servo motor to the updated position. This allows the potentiometer connected to A0 pin to control the position of the servo motor when the system is in state B. Finally, we have the serial transmission, which transmits the following template. As you can see, the code sets up UART communication for serial transmission. It initializes the UART registers and sets the baud rate to 9600. For the serial transmission, these are the registers and bits that has been enabled. The code snippet shown is being later used in these UART functions to transmit data via UART. The code snippet shown constructs a message using the SNSprintf function. The message includes a template with placeholders for autumn 2023 MX1 and student ID and the current ADC reading. This code snippet checks whether the transition enable variable is true, which then the code iterates over each character of the message and transmits it via the USR by calling the USR transmit function. This sends the message to the serial monitor for display. A 500 millisecond delay is added after transmitting each character to provide a pause between characters for better readability.
Done.
Thank you for joining us. Please subscribe. Please go to Twitch. Yeah, I think I stuffed up on some stuff.